now that we've seen where certain places are concave up and certain places are concave down on a graph, we want to think about other uses for understanding concavity. The most natural place and the most often used place for using second derivatives and concavity is actually with the critical points we found earlier. We want to look at the difference between relative maximums, relative minimums, and inflection points. Let's take a look at a relative maximum. If you look at the graph of a relative maximum, what's happening is at that critical point, the graph is also concave down. So a relative maximum happens at a critical point, and that critical point, or I should say, the graph at that critical point is concave down. The exact reverse is at a relative minimum. If we have a relative minimum, then the graph around that relative minimum is concave up. We have this parabolic shape pointed up. There is also a situation at which a critical point can happen at an inflection point. So we have three scenarios for this continuous graph. If we have a critical point on a continuous graph, then we can use the second derivative to figure out whether that critical point is a relative maximum, whether that critical point is a relative minimum, or whether that critical point happens to be an inflection point as well. This is what's known as the second derivative test. Let C be a critical value, and let the second derivative at C be defined. If the second derivative is positive at C, then the function has a local minimum or a relative minimum at that point. If the second derivative is negative at C, then the function has a local or relative maximum at that point. The second derivative test is usually a little bit faster than the first derivative test that we looked at earlier. So the second derivative test is a very useful way to quickly decide whether or not a critical value is a relative minimum or a relative maximum. You'll notice that it doesn't say anything about inflection points. Inflection points are going to happen when the second derivative is equal to 0 or does not exist, but there's also other situations that could occur, like asymptotes, where the second derivative does not exist or is equal to 0. So this test, this second derivative test, applies only to relative minimums and relative maximums. Let's take a look at a function and define the critical points and use the second derivative test to determine the relative extrema. Relative extrema, if you recall, means relative maximum, relative minimums. So we want to start out by finding the critical points and then using the second derivative. Some people take both the first and second derivative at the same time, and others take the first derivative, find the critical points, and then find the second derivative after they found the critical points. You're going to have to do both of them eventually. So what I tend to do is I tend to take both derivatives right at the beginning and then use those to find what I want. In this case, the first derivative is negative 2x plus 10. The second derivative is negative 2. In order to find critical values, we set the first derivative to 0. Remember, critical values must happen when the first derivative is 0 or does not exist. In this case, the only option is when the first derivative is 0. So I get a critical value of x equals 5. There's only one of them. The critical point happens when x is equal to 5, and then I figure out what the y value would be by plugging in the 5 into my function. In this case, I'll get negative 5 squared plus 10 times 5 minus 1, which is 24. So the critical point is 5, 24. Now, I want to determine whether or not that critical point is a relative minimum or a relative maximum. The way we do that is we plug in the value of 5 into the second derivative. In this case, there's no calculation. The second derivative is a constant of negative 2. So no matter what I plug in, I'll get an output of negative 2. Now, the important part there is that the second derivative is negative, which means that we're concave down. Because we're concave down, I know that the point 5, 24 is a relative maximum. All right. How do I know that? Well, it's got to be a critical point. So it's got to have first derivative 0. In other words, the tangent line has to be flat. And concave down means we're going to be pointed down. So I often will draw a little parabolic shape pointing downwards for concave down, just to remember that if I have concave down, then it's at the top of a hill. If I had concave up, we'd be at the bottom of a valley. So this point, this critical point, must be at the top of a hill, and therefore it's a relative maximum. So that's how the idea of critical values and using the second derivative to determine relative maximums or relative minimums work out. Notice that's a little bit quicker than having to pick a point under 5 and pick a value over 5 and determining whether we go from increasing to decreasing or from decreasing to increasing. It's just a little bit quicker, and so it makes for a really nice test.